All righty, let's see how far we can get today. So we were solving the problem on slide 40, and we got this far. Hey, Adderall gang. Okay, so we already have the magnitude of F32. So we're going to go ahead and figure out the component F32X. We figured out the angle last time, so it's going to be 53.1 degrees. All right, let's do the Y component. So we get this, but if we look at where F32 is, we see that this has to be a negative component. All right, so that is going to give us okay. And now we have two vectors, one we solved last time and now this one, that we can add together to get the total force on what were we looking for? Total force on the 1 microcoulomb charge. You could either call it total force, I'll just call it force 3, because I called that charge 3. Okay, so we go back up. What was our first vector? So it's that, so it's there. So we have a negative x, we have a negative component. It's all in the x direction. So let's remember what we're doing. So it's going to be a negative 1.5 newtons plus 0.432 newtons. And then the other vector had 0 in the y direction. The total force vector is going to give us a third quadrant vector. So then, of course, we want the magnitude of this. That is going to give us 1.21 newtons as the magnitude of that vector. Then, of course, we want to know its direction. I'm just going to call it angle phi. Okay, so it's 28.3 degrees. Now we have to start asking ourselves where that is. Okay, I'll come back down in a second. Let's look at the original figure. So you see we put the X and Y axis over the 1 microcoulomb charge. We know that we now have a third quadrant vector based off our vector addition. So let's go ahead and redraw our X and Y. Now, if I go ahead and put back in, so what this was, so that was our charge. We had a force vector that way. We had one that way. So this one was force 3-1. That one was force 3-2. And we had our angle theta there. Now, our total force vector is going to be somewhere 28.3 degrees into the third quadrant. So which way do you think it's going to go? Where do you think it's going to be measured from? The what? Negative x-axis. Yeah, because so look here. The magnitude of our x is larger than our magnitude of our y. So it's going to go further in x than it does in y. So the smaller angle has to come down. And plus, it's also a positive angle, so it's to be measured counterclockwise. So our total force vector is something like that. With our angle phi. Now, does everyone have this? Because I'm going to switch slides. Okay, where are my new ones? Okay. Okay. All righty. So the question is, where does Coulomb's law come from? Well, where'd he get it from? How? I feel like I'm sitting at that bar in Letterkenny. Just so I was asking my students a serious question the other day. So where it comes from is you're going to learn more about this in a little bit, but it's kind of an introduction. It comes from what's called Gauss's law. So Gauss's law is a way to start thinking about the electric field. So if you look over on the right, you have a point charge, and then you have a Gaussian surface. So here's the fun thing about Gaussian surfaces. That point charge is not actually inside of a sphere. That is a spherical surface that you imagine around the point charge that you're going to use to calculate the electric field as it fluxes through the surface. So of course, your Gaussian surface, your electric field should come out of it perpendicular at every point. And so if you think of this surface and each individual little element dA, these are differential surface area elements. So you see in spherical coordinates, we measure things sometimes rho theta phi, sometimes r theta phi. When we want to know the size of each one of those little elements, what you notice is we have S1, we have S2, and if you're finding out the surface area of a rectangle, how do you do it? How do you find the surface area of a rectangle? Yeah, length times width. So in our case, our differential surface area element is going to be S1 times S2. So arc length 1 times arc length 2. So we need to figure out what those arc lengths are. Well, if you think about it, here we're going the radius of the sphere out to the surface that we're looking at. And then that R is going through a d phi. So a small angle, a small differential angle phi. So what is the arc length formula? So we need our well, let's do this a different way. So it makes more sense. I don't want to do extra steps. We'll do S1 first. S1, again, your R out, you go through a d theta. So your S1 is going to be your R and your angle, d theta. We're going to go up. So to make this less steps, we're just going to use the right triangle they gave us. Where your right angle is right there. And so as that then goes through an angle d phi, your arc length becomes r sine of theta d phi. And so then your differential area is going to be r d theta, r sine of theta d phi, or your area element is going to be r squared sine of theta d phi. There is a cubical element, or not, well, a sphere, a three-dimensional element as well. But you'll find if you're as you're translating from X, Y, and Z to spherical coordinates, this element remains constant. So if you have like dx, dy, that's going to be an area. You just replace it with this. Now, let's look at Gauss's law. When you use it, you'll use the easier version, but so we're differentiating how our phi's look because I don't do a capital phi very well. So the flux through a surface, or as physics calls it, capital phi, that is going to be the surface integral E dot dA. And that's going to equal the charge inside your surface over epsilon zero. Huh? No, epsilon zero. Yep. Permittivity of a vacuum. So that's a universal constant. So if you ever see it, you just look it up. Now, we have a couple things going on. We have a surface integral, which for a surface of a sphere is going to have to end up being a double integral, because we're going to have to integrate over theta and phi. And then we have a dot product inside. So remember we talked about the dot product. Actually, we didn't talk about that yet. So here's your first type of vector multiplication. This one you're actually going to want to remember. So if you have A dot B, there's two ways you can solve this. The first one is AX times BX plus AY times BY. That's the first way to solve it. The second way to solve it that's more common is magnitude of A, magnitude of B, cosine of theta, the angle between the two vectors. So if you had A, B, that's theta. So if we think about the E dot dA, let's look at our Gaussian surface there. The electric field and dA have an angle of what between them? Look at the directions of the dA and the E. Yep, so it's an angle of 0. Cosine of 0 is what? 1. So what we have, our surface integral, the V dot dA, going to be the surface integral, oopsies, of E dA cosine of theta, which is cosine of 0. So that becomes 1. And we're going to end up with our surface integral of E dA, which is a lot easier to solve than a dot product inside of an integral. And so we can start representing this. So in general, you have Q inside the surface. So our Q inside the surface is just the charge of the point charge. So this will be Q, little q, over epsilon 0. Now we set up the fun part. So for this, our electric field is a constant. Sonia, what can we do with a constant inside of an integral? Take it out. So we have a surface integral over all of those little differential areas. Essentially, what we're doing is we're integrating the surface of the sphere, or the surface area of the sphere at a specific value for r. Which, if you remember, our dA becomes r squared sine of theta d theta d phi. The d theta d phi tells us we have to have a double integral, because we're going to have to integrate over theta and phi to get the surface of that sphere. So we'll set this up and talk about it. Then it goes 0 to 2 pi for our phi. 0 to pi for our theta, r squared, sine of theta, d phi. We don't go 0 to 2 pi for both of them, or we end up double counting some of the surface. Because if you think about it, so our theta is just going to go 0 to pi, so just top to bottom, so that theta will go 180 degrees, and the phi is going to take that and wrap it all the way around. And we get the surface of our sphere. So of course those are radian measures. There's another constant in there. Do you see it? Something else I can pull out of there. Nope. The r, because it doesn't match any of the differentials. This is when physics is fun. I'm trying to help you develop a new way of thinking. Mm-hmm. Yeah, so it's the same symbol for surface integral, path integral. It's the same symbol, but they'll mean different things. So like the circle around it means this is a closed surface. So we know we're doing a surface integral. We could do a volume integral, and it could be a closed volume. But that circle means, yeah, we're integrating over a closed pathway, a closed surface. So the way we do a double integral is first, we take care of the theta. But the whole point of this is to push you way outside your comfort zone to try to get you to think about things differently. So sine and cosines and integration and differentiation are real simple. So your integral of your sine is your negative cosine. Your integral of your negative cosine is your negative sine. The integral of your negative sine is your positive cosine. Cosine to positive cosine to positive sine to negative cosine and negative sine, just so round and around and around and around. So this one is going to become evaluated at the limits of 0 and pi, which evaluation of limits is a difference. So that means we're going to have a negative cosine of pi minus a negative cosine of 0. So we're just taking a difference. It's essentially a delta cosine theta. So there's going to be a negative 1 minus 1. That whole thing integrates to be 2. So now we did the theta part, and we can pull 2 out front. And then we're left 0 to 2 pi with the differential. Anytime you have the integral of a differential, you just get that value back. So The integral of d phi just gives us phi. Phi, evaluated at 0 and 2 pi. So remember, we're essentially taking a delta phi. That's going to be 2 pi minus 0 equals 2 pi. So that whole integral ends up being 4 pi. Because now, when we put it all together, we have our original constant, ER squared, and then we have the 2, we have the 2 pi. So we end up with 2 times 2 pi times r squared, E equals 4 pi r squared. Don't forget our electric field, E. So that is our surface integral. So now we'll say our original surface integral, after solving it, equals 4 pi r squared electric field equals the Q inside over epsilon 0. And so now we know our electric field is going to equal 1 over 4 pi epsilon 0 Q over r squared. So that is the Coulomb electric field. So we remember that force is actually Q times Q over r squared. So now we have a real convenient little equation we can get to where the electric force is going to be some other charge Q prime times the electric field. No, you don't. This is something you're going to want to remember. You're going to use it a lot. And so now you're going to have 1 over 4 pi epsilon 0 Q prime times Q over r squared, or Q1 times Q2 over r squared. So we get Coulomb's law. Yeah, so that K equals 1 over 4 pi epsilon 0. That is Coulomb's constant. Well, so you like Q prime and Q, that's just two different charges. You could call it Q1 and Q2. The whole point, the thing that so many people seem to be missing over last semester up till now is that physics is not about memorizing an equation and plugging in numbers to get your answer. Physics is about modeling the universe in a mathematical way. It doesn't matter what you can memorize and plug in. If you can't model the world around you, you can't do anything. It doesn't matter what profession it is. You're going to have to be able to present a model for the problem you're trying to solve. And when you're at the level where where you're called doctor, you have to do it from scratch. You don't have textbooks to look in anymore. So as much as you don't like it, I'm trying to help. So we talked about this, the electric field. So of course we've been working with electric force, but now we know the electric field is some charge Q multiplied by the electric field of another charge, or electric field in general. So of course your electric field will be force divided by the charge Q. And if you look here, this is a uniform electric field, not like you've been seeing. What do you has anyone ever seen a contraption like this?
It's like the electron.
So first off, your SI unit for the electric field is newtons per Coulomb. It's not a ladder. Oh, the excited states? This is an actual device you can use. No, this is a capacitor. Capacitors hold electric fields. And as you'll learn, when we put materials inside of capacitors, dielectrics, it can hold more field. You ever been by a big transformer station and you see those stacks of like porcelain, they're not discs or cones. I don't know, like little porcelain hats, just one on top of the other. Those are chained capacitors. Porcelain is a dielectric. It's increasing the electric field that can be stored in each capacitor. So here's a question. If I was to put a positive charge Q in here, which way would it go? To the right. Mm-hmm. And so the opposite, if I put negative Q, the electric force pulls it to the left. You can also think of this as your positive charges are attracted to the negative plate. Your negative charges are attracted to the positive plate. And something you'll learn that we're going to work with a lot is in between here, you have a delta V. Does anyone remember what delta V is? Voltage, but it's more electric what? If I hold an object way up high, it has what? Potential. V is electric potential. All righty. Let's work an exercise. A small sphere of mass 5.1 grams is hanging vertically from an insulating thread that is 12 centimeters long. Why is it important that it's an insulating thread? All the electric charge we're thinking about is going to be right on the end of that thread. It can't disperse over the thread to anywhere else. The sphere holds a charge of 80.2, what's NC? Nanocoulombs. The sphere is subjected to a horizontal electric field of magnitude 7.2 times 10 to the 5th newtons per coulomb. And that's going to go in the positive X direction. As a result, the sphere is displaced in the direction of the electric field. What angle would the thread make with the vertical? So here's an example of what some of your homework problems will look like. I'll give you a problem like this, and I'll probably give you the answer, and I'll give you an equation like that. And I'll tell you, draw a diagram and derive that. Let's see how we would draw a diagram for this. Well, so we have to have, I don't know, we'll just put it at some angle. And now we know that this ball has both a mass and a charge. So we're just remembering that. So that means we know that there is going to be a gravitational force on it. Your electric field is there. And you have your vertical. With your displacement, theta. The other thing that you, if you didn't take last semester, you can call it, you can name it however you want, but there is a force that's keeping this charge from continuing to move, and it's the string holding the ball, okay? So there is a force along that string that we'll call tension. These are all, this is your free body diagram for this situation. Remember, the weight of an object is always mass times gravity. It's always going to point straight down. Okay. Now there's another way that I drew this because I used it to help me solve the situation. And I'm going to take my charged sphere, put it right at the origin. Let's see here. That's my tension. There's my weight. So if I go ahead and redraw my vertical, I can put in another line that's horizontal to the x-axis, because eventually I'm going to want the components of this vector. And I know that that's displacement theta. If I draw it in this way, I also know that that's theta. So now I can find those components pretty easy when I need to. So that would be so we have components for that. Some people will have to re-practice drawing free body diagrams. The rest of you, no excuse. So the thing I'm going to remind myself of is that, well, my Tx is going to be T sine of theta, Ty be T cosine of theta. And I use the right triangle where I put the components. Now, how was I able to know that that angle theta transferred to that second location? Opposite interior angles. So now, we're trying to figure out theta. All righty. So how do we start by solving these? We have forces in two directions. Yeah, how do we do that? How do we get to there? Now, how do we get there? I was watching a video the other night where someone said, hey, it's about a square foot, and the other guy goes, how big is that? I feel like this is that situation. I don't want you plugging in numbers. So We find out our total what in all directions. We find out total what in both X and Y, total force. So let's do the Y direction. The sum of all of your forces in Y, and remember, we can keep these completely separate. So in Y, we're going to have our Y component of tension plus our mass times gravity. And if this sphere is just hanging there, what does this all equal? 0, because it's a static system. Now we think about which way everything is pointing. So that's going to be Ty minus mg equals 0. Why did I do that? Yep, mg is pointing down. Ty. So this will end up being T cosine of theta equals mg. T equals mg over cosine of theta. I wanted to do this because I looked at this whole problem and I said, yeah, there's a tension holding that sphere there. I don't know what it is. So I want to get rid of it. So I'm going to find an equivalence for it and plug it in later. So now let's do X. So all of our forces in X. Well, let's look here. So the electric field is going to provide a force. Electric force. The only other force we have in X is the X component of the tension, which will be the electric force minus the X equals 0. We just learned electric force can be plugged in as what? Q times E. Let me call it the magnitude of E minus, and we know Tx is T sine of theta equals 0. So then we can say T sine of theta is going to equal Q E. Now I'm going to take what I found for T and plug it in there. So I'm going to get mg over cosine of theta. Sine of theta equals Q times E. How do I get the tangent from here? It's the other way around. So what we do, we're just going to switch this around. So we're going to have mg sine over cosine QE. So it's going to give me mg, and that's the definition of tangent, theta. Tangent theta over mg, and then theta, of course, is going to be the inverse tangent QE over mg. Now, if you're doing an assignment, this would be what you, if I set it up this way, this would be what your answer would be. I'd go ahead and give you the answer so you could check yourself, make sure you got the right equation. But from here, now up in the problem, you have a whole bunch of numbers. We have what newtons per Coulomb, coulombs. This will have to be in kilograms, and that'll have to be in. So let's look at what all these numbers look like. Well, your charge is going to be 80.2 nanocoulombs. So that's just 80.2 times 10 to the negative ninth coulombs. Your electric field, 7.2 times 10 to the fifth newtons per coulomb over 0.0051 kilograms. And then remember that gravity is 9.80 meters per second squared. That's a constant. If you weren't here last semester, G will always equal that. Theta is going to become 49.1 degrees. That's the angle that that electric field pushes that charge to. So a couple constants, G. That's always going to be that. You need to make sure when you're putting numbers in finally that you make all the units match. And it's always best practice just to go to the SI version of units. So we go to coulombs, kilograms, newtons per coulomb, meters per second squared. But make sure you practice how to do the mathematical modeling. You will have some of those in assignments. And again, remember to actually get a good grade in this course. I don't expect perfection, I expect effort. I don't care if it's perfect or not. Give it your best shot and turn it in. And do we have assignments today? Some emailed them.
The rate,